welcome. In the last class, we have discussed the Brownian motion, and we have been discussing the displacement correlation function and velocity correlation function. So I want to just conclude that discussion in this lecture, and then we will talk about the Brownian motion of a free particle, setting ground again for the discussion of polymer solutions. So just to recall the discussion regarding the velocity and autocorrelation function, what we had derived so this is what my velocity correlation function is. Again, just to reiterate, the velocity really mean the rate of any change of any property, not really only the position, it can be any property. The rate of change is what I call velocity, just like the language that's been used here. Velocity correlation function, which I can write as half of the second derivative of the displacement correlation function as the second derivative, half of second derivative of the displacement correlation function. And just to give an example of what xi and xj can be, so xi and xj can be, for example, the change in position along x and y direction. So this would, the first term would then be change in x, second term will be change in y, and on the left hand side we would have the velocity in x multiplied by the velocity in y. It can also be, for example, position and say dipole moment. So position, let's say x coordinate can be my xi and dipole moment can be my xj, and again we can use this relation. So we can interchange this xi and xj for any property that we are looking at. So we can also write this particular relation in integral form. If I simply integrate this twice, what we should get is a displacement correlation function as an integral over the velocity correlation function. So if I do say the integration once, what I will get, if I do the integration, if I do the integration twice here, what I get is where T1 and T2 are dummy variable. T2 goes from 0 to T1 and T1 goes from 0 to T, multiplied by 2 is equal to my displacement correlation function. So I can relate the displacement correlation function to velocity correlation function in either of these two ways, either in differential form or integral form, and both of them works, and we'll use that correlation functions later in the class. So before that, I want to now talk about a slightly different concept, and we will come back to the idea of correlation functions eventually. And these concepts that I have covered so far will be useful in what we will discuss. So now I want to talk about the Brownian motion of a free particle purely from the perspective that we are used to. So, let us say we want to start from what we typically use in a macroscopic description, and then using that we want to establish what should be the case in a microscopic description of Brownian motion, and this therefore will set the ground for like what we will discuss in the case of polymers later. So, we want to discuss the Brownian motion of a free particle, and the system that I have in mind is, let us say you have some volume where it is, I mean like some vessel, the vessel shape and size and everything is inconsequential here. The key point is that it contains some solvent and just one particle, a solute particle that is moving in the solution. That is why we call it a free particle. So, it has a particle that is moving in a solvent. So, solvent can be represented, for example, by teeny dots which are much smaller compared to the solute particle, and of course there are many of them, and this is my solute. So, if I think of the motion of this particle, if the particle is large enough, we already have said that the Brownian motion is insignificant, that is the velocity of the particle due to thermal fluctuations is very limited. In this case, since I have taken just one solute particle, it is not undergoing any collision with any of the solute particles because they are not present. The only thermal motions it is getting is because of collisions from solvent molecules, right. So, if I really zoom in there, what I would see is we have this solute particle surrounded by solvent molecules which are bumping into it. Of course, not all of them, they are bumping into it, and because of this bumping it is getting some thermal motion or fluctuation in its motion, and the solute also can have some motion V that again can change in direction with time, because at every moment it is experiencing a different configuration of water molecules around it, or different orientation of water molecules around it, or different momentum of water molecules around it. So, the collisions it experiences at every time is different, and therefore, the motion of solute molecule can be somewhat fluctuating in nature. Again, as I was telling in the case of the Brownian motion discussion in very beginning of the last couple of lectures, that although it appear to be random, it is not quite random, although we will use a random function to represent it. If we really can solve the equation of motion of all the solute and solvent molecules in the system, in principle we can get a fully deterministic solution. The only thing is that it is computationally very intensive to do, and of course, that is the idea that we do in the molecular dynamics that we can do for smaller systems. Okay. So, if we cannot do that, then we can do some math, and that math turn out to be quite simple, but yet very useful. Okay. So, this solute molecule is surrounded by these guys, and as I have already said, if solute molecule is large enough, then in that case we know how to characterize the motion of the solute molecule. We have relations like say Stokes' law that tells me that the force acting on the particle or the drag force acting on the solute particle is equal to some constant zeta multiplied by V. This is in the limit of very low flows and it is referred as Stokes drag. Of course, we are going to no flow situation in a moment, but let us start with the case when it has some drag because of this. And then this zeta is referred as friction coefficient and for a spherical particle of radius a in liquid of viscosity nu, we have the Stokes relation zeta is equal to 6 pi eta a. If it is not spherical, we can have some other value of zeta, but that is not really very important. The main thing is that the solute motion will be resisted by the presence of the drag, that is due to the solvent molecules in the system. Now, of course, there can be other force that can give rise to a net motion, but let us say we are looking at equilibrium, then the other force is absent. Then the only force for macroscopic particle is the drag force. We haven't yet talked about the thermal forces yet, but apart from the thermal force, we only have a drag force. If there was some external force, then that would have caused the motion, but let us imagine that there is no external force, we are at equilibrium. So, at equilibrium then assuming that we do not consider the thermal forces yet, we have this relation which is true for large particles when effect of thermal fluctuation So, by the way, how large is too large, and we have already done some scaling. In fact, if it is like greater than 1 millimeter, it is already very large particle. Only when we go to say a micron range, then the thermal motion become appreciable. Otherwise, the drag force is all that is acting on the system. So, if you are having difficulty looking at how the system, how the solute molecule can be moving if there was no force acting on it, you can assume that let us say the motion was occurring in the previous time, the force was being applied, and then at time t equal to 0 we stopped that force, and now the only force acting is the drag force. So, we may have started with a velocity that may have been due to a previous motion, but now that velocity, that external force is absent and we only have the drag force acting. So, if we only have the drag force acting, and if I solve this equation, what I would get is V is equal to V naught exponential of minus t by some constant tau v, where tau v is given as m by zeta. Okay. So, V naught is my initial velocity. What this pretty much means is if I start with a velocity of say v naught, it would rapidly decay to 0 with time t by an exponential kind of a decay, and the system will cease to move. Okay. So, for a large particle this is indeed the case, the system will cease to move and then there is no motion. But if the particles are like now smaller in the micron range, then something else should be present in this equation to make the motion happen, the motion that we attribute to the collisions it is experiencing from solvent molecules. We must have a term in the equation of motion that should give rise to that fluctuating motion that is occurring because of the collisions from solvent molecules. So, one way to do that is apart from the drag force, we also include some other force that is a function of time, and that force will keep on moving the system even when the drag force, the velocities goes to small value, then also this force will always exist that will lead to that kind of a motion that we have. So, it is not always, zeta v is always dissipative, Fr is not a dissipative force, this is a force that is giving rise to the fluctuating kind of a motion that you see in the actual system. So, for small particles, so let me put a number, say 10 micron, but in any way this is really something that you have to do the math for every diameter. Thinking of like Brownian motion below say 10 micron, I would say it will be appreciable. The lower we go, it will be more and more appreciable, but if we go to say nanometer range, we will not be able to observe it, and then we do not call it a Brownian motion, we will simply call it a thermal motion. Let us say for at molecular level, we do not call the motion of molecules due to collision as a Brownian motion, we simply call it a thermal motion. The Brownian motion we attribute in the limit when we can see through a naked eye or through a microscope some random motion of the molecules, because that is how it was observed originally by Robert Brown. Okay. So, now we can include this random force Frt, but we do not know what that force should be, but we know something for sure, that this force should not have a net directionality, because let us say if the force is always in the horizontal direction and always to the right, then this will lead to the motion of the sphere to the right, then this would be same as an external force. The whole notion of Brownian motion is based on the idea that the molecule fluctuate around its position because of the frequent collisions. The forces are not really constant and they do not apply in just one direction, they should be able to change directions. Okay. So, one attribute we can think of having is this force must have a mean value of 0 if I take an average over time, or if I do an ensemble average over many particles in the system. Okay. That is one attribute. Now, if the mean value is 0, then how do we characterize the strength of the force? The strength we characterize using again the idea of the autocorrelation function we have discussed. So, although the force has a mean value of 0, it does not mean the force does not exist at any particular time. It can have say fluctuations around 0, and we can talk of the strength of the force by looking at the correlation between points t and t prime. So, now I want Frt, Frt prime to be non-zero. Now the question is, non-zero means what? I mean, like ultimately it doesn't provide an answer of what that value should be, and one of the good approximations can be that we represent using a delta function, because eventually when t becomes t prime, then it becomes FRT squared, and that clearly is a large value, and the correlations must decay at long times, because after some time the system will lose its memory. So these correlations will not exist permanently. After certain time scale, the correlations must die out, and therefore we can approximate possibly by a delta function, not really the force but the correlation of the forces. Now the question is, like, how do we get this quantity A, and that's what we can do now. Okay, so we want to get the value of A. So until so far we have assumed that the force, we don't know what FRT is, but the mean value is 0 and the correlation value is given by this particular function. So now we want to get the magnitude of A, and to get that we want to use the definition that we started with. It comes from equipartition, that the square averaged of the average of the squares of the velocity must be equal to kBt by m, again ignoring the prefactors, and using that we can then get the expression of A. So let us get started on the derivation. I will complete in the next lecture. So what we want is we want to start from here and then try to use this relation to get the expression of A. So in here I want to ultimately write not in terms of FRT but in terms of FRT prime, because the relation we have assumed is for FRT prime. Okay. So now this is, if I look at just the first term on the left hand side, right hand side, this becomes that, and I know how to solve it using the linearity, the linear ODE that we have on the left side. So we have d by dt I am sorry, there is a by m here. So this equation we have got. If I multiply both sides by e to the power t by tau v, and now you can see, if I take a derivative of this, this is what I am going to get, because this term is simply 1 by tau v. Okay. So we will start from this particular point in the next lecture and then get the expression of A that we had in our relation we have assumed for the autocorrelation of FR T, that is the random function that we have introduced to characterize the Brownian motion of the free particle. So with that I conclude this lecture. Thank you.